Good morning, everyone. Welcome to the Pico-Seminar series, which is part of our Pico Electrodynamics Theory Network. So the aim of this network is really to bring in the diverse researchers working in the area of the microscopic electromagnetic fields, really like looking into bridge the gap between the researchers involved in the topological electronic band structure, like the quantum materials, quantum optics, density functional theory, nanophotonics, and computational electromagnetism. So we had several wonderful talks last year where we brought in researchers working in like different areas where the atomistic light matter interaction phenomena manifested into many of the observations. So we are reinitiating this effort again this year, and we have a wonderful speaker again this year, Professor Ashwin Ramasubramaniam from University of Massachusetts, Amherst. Now, Professor Zubin Jacob will introduce him. Thank you.
Great. Thank you so much, Satwik. And as Satwik mentioned, we are kickstarting 2023 with Professor Ashwin Ramasubramaniam. And he's going to talk to us about first principle simulations and also really understanding 2D materials in more detail. Just a quick introduction. So Professor Ashwin Ramasubramaniam is a professor of mechanical and industrial engineering at the University of Massachusetts, Amherst. He obtained his BTech in mechanical engineering from IIT Bombay and then his PhD from Brown University. So he's a recipient of many kind of famous awards, most notably the very prestigious DOE Early Career Award in 2013. So, and his area of interest is very broad, all the way from continuum mechanics and molecular dynamics to computational methods such as density functional theory applied to materials across various scales. So with that, I want to welcome Professor Ashwin Ramasubramaniam to the Pico-Seminar series, and we are looking forward to hearing his exciting research. Thank you.
Thank you, Zubin. Thank you, Satwik. It's a pleasure to be here. Thanks for the invitation, and thanks to everyone who can make it to listen to my talk. So I'm going to talk a little bit today about some very recent work, actually, related to hybrid materials. So these are two-dimensional materials that are combined with zerovalent metals specifically, that find unique and interesting applications in optoelectronics. And before I jump into the talk, let me just thank my collaborators over here. This work is done in collaboration with Doron Nave, who's at Bar-Ilan University in Israel, Christy Koski, who's at UC Davis, and Francis Deepak, who's a scientist in Portugal and leads the microscopy and characterization laboratories at their national facility. And this work was funded by the NSF and through a joint NSF-BSF grant with computational support from XSEED. So before I jump into my talk, let me just tell you very quickly about the kinds of things we're interested in. We're interested in a broad spectrum of behavior in materials that span the range from optoelectronic properties, spintronic properties, all the way to thermal management, catalysis, and more recently, some work that we've been doing in integrating organic, inorganic materials to make novel, flexible electronics. So my focus specifically is in density functional theory, atomistic modeling, in terms of whether it's Monte Carlo or molecular dynamics, and then some ongoing interest still in the continuum mechanics of these. And really, it's in trying to understand how to live at interfaces between chemistry and mechanics, between mechanics and optoelectronic response of materials, and so on. So what I'll tell you about today is related to some degree to this figure that you already see on the left over here. This is an example of what is called a misfit layered compound, which consists of alternating layers of a 2D material and another 2D material over here. And neither of these materials can exist by themselves, but they only exist in this kind of a unique structure, unique layered structure, which is stabilized by charge transfer interactions. So there's a whole class of materials like this, layered materials, intercalated materials that are extremely interesting with all kinds of interesting physics and chemistry associated with it. And today I'll focus on something less exotic, but really just talk about intercalation compounds. And specifically, I'll focus on MoS2. So for those of you that might not have heard much about this before, let me just tell you very quickly what we're looking at over here. So the basic idea of intercalation compounds is not new. You've definitely heard of this. You've definitely even encountered this in practice. Think about a graphitic electrode, right? Where you have in a battery, where you have an intercalant, which is the ion moving in and out of the electrode. So intercalation compounds have been known for a very long time, okay, going back to the 1800s. And in the earliest form, they were known as graphitic intercalation compounds, okay? There is this nice review from 2019 that really, from which I've borrowed this figure, that really talks a lot about these various stages in the field and how they've been developing and where we are right now. So anyway, this history is old. Initially, this was in the phase of discovery. And then somewhere in the 1900s, you can see around 1960 or so, here people started not just characterizing these to try and understand their interesting and unique properties, but they also started finding applications, for example, in batteries, right, which is one of the most obvious applications one can find for these. But with this resurgence and interest in the 2D materials field over the last 10 to 20 years, these intercalation compounds have again become very interesting, and people have started studying them for all kinds of different systems, including, let's say, intercalated topological insulators, where you can intercalate metals into them, where you can intercalate other maybe oxide semiconductors into them, and so on, where you can actually even do chemistry in the gap, where you can intercalate one species and then subsequently perform some kind of chemistry to form a different compound or a different phase in the van der Waals gap. So there are all kinds of different angles to this, and intercalation has been used, or is being used widely as a strategy to tune optoelectronic properties, to tune plasmonic response, and to stabilize exotic phases via chemistry within the van der Waals gap. So again, the confinement becomes very important over here in stabilizing these phases that would not normally exist as independent, isolated phases. Okay, so in today's talk, what I'm going to talk about is copper and tin intercalation in MoS2. So again, fairly simple systems. MoS2, a fairly well understood by now van der Waals material, or a layered material, if you want to call it that, and copper and tin, nothing particularly exotic about this. But once you start putting them together, interesting physics emerges, and that's the purpose of today's talk. So before I jump into it, let me just say very quickly what zerovalent intercalation involves. This is the work of my colleague, Christy Koski at UC Davis, and she has a very nice article over here, including a manual that is available on our website that actually tells you how to make these intercalated compounds, detailed recipes for making these. It's done by solution processing, nothing particularly exotic, fairly straightforward and simple, but you can get all kinds of interesting things using these simple recipes. And over here, you can see these colored boxes over here are the intercalants that they've been able to introduce into many host lattices, okay? Transition metal dichalcogenides, bismuth selenide, variety of other compounds. So the basic idea over here is that we're intercalating zerovalent atoms and not ions into the van der Waals gap. So in a battery, right, you're intercalating, for example, lithium ions in and out of the gap. This is different than what is going on over here. So here, what is happening is basically it is reduction or redox reactions that are taking place in solution that produce these dilute zerovalent atoms. So copper 0, for example, not copper 1+ or 2+, or whatever the case may be. And as long as this is a dilute solution of zerovalent atoms, then the driving force for intercalation into the van der Waals gap is greater than that for agglomeration. If the concentration in solution becomes too high, you start forming nanoparticles. This is not what you want to do, okay? But given these conditions, you can actually drive these copper ions into the van der Waals gap, since the Gibbs free energy for intercalation to be in the van der Waals gap is lower than for them to be in solution. And this is a low temperature solution based technique. One does not have to go to high temperatures. High temperatures have been used for solid state diffusion before, nothing new over there. But this can be done in solution very easily with large microscopic crystals of these materials. And there is really a wide range of tunability, as you can see, in terms of what can be intercalated and the whole gamut of layered materials that is available to us these days. So, for example, one can make chemically tunable layered materials that show chemochromic behavior. They show interesting superlattices that one could not just synthesize readily by other methods. They show charge density waves. For example, if you're using something which is superconductor like niobium selenide, then you can introduce metals into the van der Waals gap and then play around and tune the charge density waves in these materials and so on. Okay, So today, I'm going to look at these two particular hybrids. So on the left-hand side is copper-intercalated MoS2, and on the right-hand side is tin-intercalated MoS2. These are synthesized by Professor Koski. The characterization is done by Dr. Deepak at Portugal. And my colleague Doron Nave takes all of these and makes IR detectors with them. So I'll try and tell you a little bit, give you a little bit of flavor of everything that goes on in this particular project. I'll focus on the first principles part for the most part. But anyway, these two figures over here are essentially at the heart of what we're talking about. So what you can see right here are planes of MoS2. This is a van der Waals gap. And in the van der Waals gap, you can see right here, faint gray specks. This is the copper. And here are the peaks more clearly resolved. These are the molybdenum atoms sitting over here. And this is the copper intercalated in the van der Waals gap. And you can see in the case of copper, you get actually pretty nice continuous, almost contiguous layers in the van der Waals gap. Here's the case of tin. Again, it's been colored in this particular inset over here. So the yellow is the sulfur on the top and bottom planes of MoS2. And in the van der Waals gap intercalated over here in red is tin. So you can see the tin over here. Again, one gets fairly large amounts of tin intercalation. But the difference between tin and copper is that in the case of copper, you can get nearly contiguous layers of copper in the van der Waals gap. But in the case of tin, they tend to be patches. They may be large patches, but at no point have we observed almost contiguous monolayers of tin in the van der Waals gap. And this becomes important subsequently, as I'll point out to you. Okay, so basically, this is the intercalated material. So they start off by growing MoS2, vertically aligned MoS2 in a via in p-type silicon. They intercalate the MoS2 with copper or tin, and then put an ITO electrode on top. Okay, so you basically now have a PN junction, and one can do photo detection, etc. with this, as I'll talk about briefly. Okay, going to models. So I'll talk about theory now for a few slides and what we do in terms of modeling to understand these materials. So the first question, of course, is a structural question. What does copper, or what does a monolayer of copper in the van der Waals gap look like structurally in terms of its electronic properties and so on? So the simplest thing you can do is to start off by putting one copper atom in there and realize that it coordinates tetrahedrally to the sulfurs from the neighboring layers. Now, this is not thermodynamically favorable for a couple of reasons I'll talk about briefly. But anyway, assuming one knows that, then you can say, let's look at all the tetrahedral sites that are available. Let's put copper over there so that you basically have the same amount of copper as you have MO in the MoS2, in one MoS2 layer, and then ask ourselves what the copper does. And here's the result of that exercise. So if you put in about one copper per formula unit of MoS2 in the gap, it spontaneously breaks up into these kinds of isolated clusters. Okay, so what this is telling you, of course, is there is a driving force for copper to agglomerate in the van der Waals gap. So in other words, the binding energy of copper is stronger than the copper cohesive energy, is stronger than the energy of interaction of the MoS2. But still, the MoS2 planes are critical in stabilizing that discontinuous patchy monolayer of copper within the van der Waals gap. And now there's still more room for copper intercalation. And so here's a more realistic model where one sees that for a 4x4 MoS2 supercell, one can actually put in a 5x5 monolayer of copper. And if you do that, it actually stabilizes as a nice, close-packed layer of copper. Close-packed layer of copper within the van der Waals gap. But even here, if you look at this, the side view, you can see that the copper layer is slightly corrugated. Okay, so this is not a copper layer that is completely non-interacting at this point with MoS2. There is still some slight chemical interaction between the sulfurs of the MoS2 basal plane and the copper. And this becomes important, anticipating its optoelectronic response subsequently. Okay, so a little bit about the energetics. We use density functional theory, and we use DFT-D3 dispersion interactions to be able to model the van der Waals forces between the layers correctly. And you can calculate what it takes to start intercalating copper in the van der Waals gap. So if at very dilute concentrations, you can see that the intercalation energy is very high, right? And this is basically the energy cost for wedging copper into the gap at low concentrations. MoS2 by itself is perfectly happy. The monolayers are sitting, they're sort of sitting in this AB stack, interacting with each other through van der Waals interactions. And now you're trying to wedge copper in there and open up that space between the monolayers. This is destabilizing. And so you have to pay a high energy for this. Okay, but as you start intercalating more and more copper into the van der Waals gap, you see that the intercalation energy goes on decreasing monotonically. Okay, so basically, once you've paid that high energy cost initially to wedge the copper into the gap, then it becomes easier to start intercalating more and more coppers as you've opened up the space between the layers, roughly speaking. You can also see that the layer spacing increases monotonically as you go on intercalating more and more copper into the van der Waals gap. And all of this can be quantified, of course, through microscopy, right? One can go in here, one can measure the average interlayer spacing, etc., and indeed see that with increasing copper intercalation, that interlayer spacing increases from the fringes. Okay, so now here's where it gets interesting. So in terms of electronic structure, I'm going to talk about two cases up here. One is this patchy copper that you see up over here, and the second is this contiguous monolayer of copper intercalated in the van der Waals gap. So the first thing you see from the density of states over here on the top, in red, I'm showing you the total density of states, and in green, I'm showing you the MoS2, and in blue, the copper density of states decomposed. Okay, total density of states projected onto the MoS2 or onto the copper. All of these calculations, by the way, are done with the HSE hybrid functional, since we know that the PBE functionals underestimate the band gaps of MoS2 severely. The HSE is not exactly correct either, but it gives you a slightly better estimate of the band gap. It opens it up. Anyway, so we see a couple of things over here. First, the band gap of MoS2, in this case, it's bulk MoS2, bulk-like MoS2. The band gap should be about 1.3 electron volts or so. And so there should be no states really right near the Fermi level right here. And you're beginning to see this broad continuum of states right near the conduction band edge for patchy copper. If you go from this sort of patchy structure of copper to this more contiguous 111 monolayer of copper, you begin to see more sharp resonances within the van der Waals gap of the material. Okay. One can also figure out electronically what is going on in terms of charge transfer interactions. So it turns out, this is not entirely surprising, that the copper donates charge to MoS2. In this case, it donates about 0.18 electrons per formula unit, whereas for the 111 layer, it donates about 0.08 electrons per formula unit. And the reason basically, it goes back to what I was saying before, which is that the copper interacts with the sulfurs, basal plane sulfurs of the MoS2. And so at low concentrations, there is some chemical bonding that's taking place between the copper and the sulfurs, and this is where the charge transfer is happening. Okay, because of these chemical bonds. But as you go to this continuous 111 monolayer of copper, the copper sulfur interaction actually becomes weaker, and the copper interaction is stronger. So the cohesive energy of copper is stronger, and it tends than the bonding energy between the coppers and the sulfurs. And so this is why that interaction becomes weaker. But still, there is some charge transfer taking place from the copper to the MoS2. So in effect, the MoS2 is being end-doped. Okay. And so going back to what I was saying about the photodetectors, which I'll talk about later, it's not just native end-doped MoS2 that you have over here. You have MoS2 that is further end-doped by copper to give you the N-type semiconductor over here. And then we have P-type silicon in our devices. Okay. So one can also go through now and calculate the optical properties of these materials through density functional theory. And I'll focus on fully copper intercalated MoS2 over here, since this is more relevant to what we're seeing in experiments. Okay, so what is most interesting in the calculated yields response from DFT is this peak over here. Okay, in the MoS2 plus copper hybrid, we see a nice yields peak emerging at about 1 electron volt. And this is a plasmon peak that can be confirmed by looking at the real part of the dielectric function. So that's where it has a zero crossing with positive slope. Okay, so that's where one can look to identify this particular plasmon peak. Now, MoS2 by itself does not have any plasmons over here. This is well within the band gap of MoS2, right? And neither does the copper monolayer. So this plasmon that is emerging over here is an emergent property of this unique Cu-MoS2 interface. Okay. If you look at the patchy copper that I was talking about before, one sees an yields response over here that is much broader, and one does not see this sharp resonance around 1 electron volt like one would expect. This is a theory prediction, of course, and the question is, do you actually see this in experiment? And the answer is yes. this is the measured yields. Okay, so our colleagues went back and measured the yields of their copper intercalated samples, and over here at about 1.2 electron volts or so is where one sees the yields peak in the actual physical samples. And now the rest of this is not captured accurately, of course, because the actual material that you have over there is not completely copper intercalated. There's not copper in every van der Waals cap. There's copper in some van der Waals caps. There's partial copper in some other van der Waals caps, and so on and so forth. So you get a mix of these sorts of responses of contiguous layers versus patchy layers versus parts that are not intercalated with copper, and so on and so forth. Okay, so one cannot expect to capture all of this, but the presence of this yields peak over here is robust, and it is robustly predicted by our calculations. Okay, one can also calculate the absorption, and here you see the nice feature about this particular hybrid. You begin to see enhanced absorption in the IR, and if you ask where that is coming from, that is essentially coming from the copper monolayer. Okay, one can again isolate the various contributions to the absorption in these particular hybrids. Let me remind you that MoS2 will not be absorbing down over here because it has a band gap of about 1.3 electron volts for the bulk. All of this response that you see over here in terms of absorption is largely coming from the copper, and then a little bit from the MoS2 because now you don't have pure MoS2, you have this MoS2 that is partially bonded chemically in some way with the copper. Okay. All right, so let me talk about tin very briefly. Now, tin is interesting in a different kind of way. So we did the same sorts of calculations that we did for copper with tin. Tin is a much larger atom, and so you can at most accommodate one tin per formula unit of MoS2 in the van der Waals cap. So here's an example of a continuous layer of tin, and here are some of the patchy tin clusters that one can look at. And we do the same exercise as before, where we see that the intercalation energy for that first event of tin intercalation into the van der Waals gap is really high, because now it's even higher than copper because tin is a much larger atom. But once you wedge open the gap, so to speak, it becomes easier for more and more tin to intercalate, and one can sort of go to the monolayer limit, by which point you can see that the intercalation energy is fairly low. The van der Waals gap is also expanded by tin intercalation, and it increases very rapidly initially because of this large wedging tin atom that you're intercalating into the van der Waals gap, and then it saturates pretty quickly once you have wedged open that gap to accommodate more tin. Now, if you look at the optical response over here, we see that tin once again, so the electronic structure itself, tin n-dopes MoS2. We see these sorts of gap states again emerge right near the conduction band edge, and this is mostly from tin and then some participating states from MoS2 because of the chemical bonding between the tin and the MoS2. And as you go to contiguous monolayers of tin, you begin to see these sorts of resonant gap states emerge over here, but there's still more of this broad continuum that one has close to the conduction band edge. Now, if one looks at the absorption, okay, once again, you see that this tin MoS2 hybrid is absorbing in the infrared. MoS2 by itself is not going to absorb in the infrared. The tin layer by itself, if you calculate its optical properties, really does not absorb down at these energies, but this hybrid does. Okay, this is subtly different than copper. Copper would absorb down at these energies or these wavelengths, but the tin monolayer does not. It is a tin hybrid that does. And one can look at the yields again, and if you look at the yield spectrum over here, you begin to see the emergence of new loss peaks in this 1 to 2 electron volt range. So this peak over here and this shoulder over here in particular at about 1.5 or 1.6 eV, that shoulder is reproduced in the measured yields over here in the experimental measurements made on these tin intercalated samples. This peak is not well resolved down here because there's a lot of background that could not be subtracted out properly. Okay, so what are the implications now if you want to think about devices? So I'll say at the outset that I'm not a device engineer, but I'm going to do my best to represent the work done by our device engineering colleagues over here. So as I said before, what we have is p-type silicon, vertically aligned MoS2 over here that is intercalated with tin or copper, and then an ITO electrode on top. Okay. Photodetectors are fabricated from this. These are reverse biased PN junctions, and then measurements are made, optical measurements are made. So let's start looking at the copper MoS2. So on top over here, I'm showing you the responsivity. which is basically the input-output gain of the photodetector system. So in this case, it is the amperes, the current per watt of incident power. So the first thing you see is this is what it is for just bare MoS2 if the MoS2 is not intercalated with copper. But on intercalation with copper, the responsivity is much higher, okay? An order of magnitude or 2 higher. And here is the responsivity resolved by wavelengths. This is 850 nanometers. And one basically sees that there are not too many differences in the response between the MoS2 and the MoS2 copper. It's just that the responsivity is enhanced when copper is intercalated into the van der Waals gap. And when you get to about here, right, about here, you can see that, so it's 1 to 1.2 microns, you can see that this drops off pretty sharply. And this is basically the, you're getting to the band gap of MoS2. Okay, so you should not see much more response beyond this point. So essentially what copper is doing is to enhance this responsivity of MoS2, or increase the gain, if you will, by an order of magnitude over this wavelength. Tin is very interesting on the other hand. You see that the responsivity is not just increased, but you also sort of see this anomaly over here with power, where the responsivity is not monotonically decreasing, but it shows this sort of hump over here, which we suspect is due to thermal effects arising from these small tin clusters that are present in the MoS2 gap. But more interestingly is if you look at this second figure over here, which shows you the responsivity as a function of wavelength. Okay, so the blue is the MoS2 and the red is the MoS2 tin. And you can see that the two spectra are completely different. It is not simply the blue spectrum that is enhanced by some amount, like you see up over here in the case of copper. And in both cases, of course, you see whether you intercalate copper or tin, you're seeing a gain. You're seeing a fairly large, a substantial gain of a few orders of magnitude of the device. So what exactly is going on over here? So our current interpretation of the results based on our theory and the spectra, looking at them in combination, is that in the case of copper, what one is really seeing is a plasmonic enhancement of the responsivity. Okay, but in the case of tin, we are seeing a response deep into the IR. It does not cut off over here just like copper does. In fact, we have cut this off at 2 microns over here. It goes much longer, you know, all the way to about 5 microns or so, but at which point there's too much noise to still resolve this cleanly. And so we're not showing that data over here. But tin definitely shows a response deep into the IR. There is some plasmonic enhancement coming from the tin islands, but essentially what appears to be happening in the case of tin is an internal photoemission mechanism that is being enhanced to some degree by this plasmonic enhancement. And why do I say that? It's essentially by looking at this. Okay, so if you take the calculated absorption spectrum, the calculated yields, and then we put the measured responsivity, we see that the measured responsivity actually quite nicely tracks this this absorption. And it also, so look down here, for example, between 1.5 to 2 microns. Here's the absorption, and here's the responsivity. It's high absorption, high responsivity. Okay, there is an anomaly over here, an unresolved anomaly over here. But as you go back to the left of this sharp dip, you see that it picks up, but it's now picking up in the regime where we saw plasmons in the yield spectrum. Okay, so there is some plasmonic enhancement going on over here. So in a sense, what we think is happening in the case of tin is that you have these islands of tin. These are not contiguous layers of tin anymore, that are forming this metal semiconductor interface, and one is able to excite hot carriers from tin, from these large patches of tin into MoS2. Now it's also interesting that this metal semiconductor interface is not like a Schottky diode, right? Because in that case, the carriers would have to drift across a potential, across an energy barrier at the metal semiconductor interface. Instead, over here, the metal is parallel to the MoS2, and the carriers are drifting parallel to this interface, which is why it's also very efficient in terms of exciting these photocarriers from the tin to the MoS2 and then gathering them at the electrode. So the drift is not impeded by these energy barriers across the metal semiconductor interface. Okay, so that about sums up what I have to say on this particular topic today. So just to conclude, I've shown you a strategy for facile intercalation of zerovalent metals into MoS2. It allows us a lot of freedom in tuning the optoelectronic properties of these materials. There are emergence of new plasmonic features, metal semiconductor interfaces, emergence of hot carriers in these systems under excitation. There is enhanced absorption for these particular systems in the near to mid IR due to all of these gap states that appear close to the conduction band edge of MoS2. And I showed you some demonstrations of highly responsive and compact near mid-infrared photodetectors. And lastly, this strategy can be applied widely across a host of, well, a host, no pun intended, but a host of host materials and guest intercalants. So we really have a large palette to play around with here. And there are lots of prospects for understanding interesting things like order disorder transitions in essentially what are 2D metals, magnetic ordering in these structures, and so on and so forth. So with that, thank you for your time and attention. Thank you, Satvik and Zubin, again for this invitation, and I'll be happy to take questions.
Great. Thank you so much, Ashwin. This was interesting. I definitely want to understand this intercalation in more detail. So I'm really happy for you to be here. So once again, Satvik, thank you for organizing everything. And thanks to all the audience members for being here. We will now go ahead to the closed door informal chat session for this talk. Great. Thanks.